After we observed the prime factorization extremely slow for large integers, so we have to get around it. Yeah. So the solution, the key of the solution, this very simple algorithm, we call it division algorithm, integer division. Yeah, so simple. Yeah, so simple, but so powerful. So with this simple algorithm, we do not need to do any prime factorization. So we can find, any two big integers, 1,000 digits, we can find the prime factorization quickly. Yeah. All right. So how do we apply this division algorithm? So this is the size reduction formula. Size reduction, based on this simple transformation. Yeah. When we look, because when you try to get a common factor, the role of the common factor in a fraction, you can use it to simplify the fraction, right? Cancel out the common factor to simplify the fraction. Yeah. All right. But when you do that, cancel out common factor, the integer part does not change anything in the common factor part. That's the important observation. Yeah. Integer part, 1, 2, 3, doesn't matter. Okay? Yeah. Then based on that, so you can throw away that integer part. Yeah. Throw away that integer part. When you throw away, you reduce the problem size. Yeah. So that's the fundamental reason, so we can reduce the problem size. And it's a variable size reduction. Yeah. Every time the size reduced could be different, a variable size reduction. Sometimes more, sometimes less. Yeah. All right. Now we are ready to write our algorithm. So the last step, we just write our algorithm explicitly. Yeah. All right. Yeah. That's the famous Euclid's algorithm. Yeah. So many of you heard of the Euclid's name. Very important mathematician. Yeah. Euclid. So the famous, he wrote a book, famous, the volume, several volumes of the book, Yeah. I have that copy. Yeah. Very old books, several volumes. Yeah. Euclid algorithm was included in that. Yeah. All right. The rule is this. All right, GCD of two integers. First, you need to make sure these two numbers cannot be both 0. If both are 0, you need to output some message, error message. After that, then if y, because this one, you want to make sure x greater or equal to y. Okay? Greater or equal to y. Yeah. Otherwise, you swap. Yeah. Make sure the first parameter is greater or equal to the second parameter. Yeah. Then you check y. If it equals 0, you return x. Yeah. But that's after the first checking. We need to make sure both not equal to 0. Then, if x mod y, yeah, so you do integer division. Here you do integer division. Yeah. X percent y means the remainder, right? Yeah. So because this operation means you take the remainder. But if the remainder equals 0, that means x is a multiple of y, then the GCD of these two numbers is just a smaller number, y. Yeah. X larger, but x is a multiple of y. Then the greatest common divisor is the y. Yeah. Simple. Then the last case, if none of the above is correct, then the last case, recursion. Yeah. You call the same function GCD, yeah, but you do size reduction. Yeah. Yeah. You bring down the larger number x. Yeah. You replace larger number x by this remainder. Yeah. Remainder we know, do you remember the definition of the remainder? Remainder must be strictly less than y, right? Yeah. When we define remainder, remainder must be strictly less than the divisor number. Okay? Yeah? So then, y, we know, must be higher than that remainder. Yeah. Yeah. But we bring down the problem size. Yeah. Yeah. Recursion, yeah. So at the end, yeah, because we have to stop somewhere. At the end, you will hit this case. The first parameter will be the multiple of the second parameter. Eventually, we will get that. Okay? Yeah. Because the worst case, when y equals 1, x is a multiple of 1, you have to stop, right? Yeah. Yeah. So you cannot do this kind of recursion forever. Yeah. Yeah. Because the worst case is y equals 1. You can stop. Yeah. Okay? Because that's the last step. When y equals 1, you have to stop. Yeah. Yeah. So you don't worry about, because when you have an algorithm, you need to consider the termination issue. If your algorithm can terminate or not. Yeah. Because some algorithm cannot terminate. Keep running forever. Yeah. You need to avoid that. Yeah. Here we know, make sure it can terminate. Yeah. Yeah. All right. Yeah. All right, so that's the implementation. So simple. Yeah. But this algorithm is so famous, Euclid's algorithm. So in number theory, so this algorithm, you know, in the foundation part, yeah, there are several fundamental theorems, yeah, including this one. Yeah. Yeah. Very useful. Many advanced results are derived from, you know, so this Euclid's algorithm, the previous slide, division algorithm, yeah, yeah, used to build the foundation of the number theory. Yeah, very important. Yeah. Yeah. All right, so that's the, you know, yeah, this question. Yeah. All right. Yeah. So now let us move to our new topic today, part C, Fibonacci numbers. I use that to give you an example, yeah, but this time we need to study, yeah, you know, Fibonacci numbers completely. Yeah. Yeah. All right. Fibonacci number. introduction to Fibonacci numbers. Properties. All right. Yeah. So now, it's a simple example, Fibonacci numbers, but we can learn many important properties. All right. Question, problem number 11. Calculate Fibonacci numbers. Let me give you the problem description. Given recursion formula, initial values, two initial values, f0 equals 0, f1 equals 1. Then, the recursion formula, f sub n equals f sub n minus 1 plus f sub n minus 2, for n greater or equal to 2. All right. Find the Fibonacci numbers f sub n. So for any, here, this means for any given integer n, you need to find the Fibonacci number for that n. When n relatively small, it's easy. So here the question is, when n is very large, then how fast can you find the Fibonacci number when n is very large? Let's answer this question. All right. Yeah, the first few Fibonacci numbers. Okay. All right. Yeah, so our plan, the first time we want to solve it algorithmically, so from our computer science point of view, we need to write a program. So we need to develop some calculation algorithm. So algorithmically, the first round. The second round, because this problem is it is a math problem, right? Solving equation, solving a recursive equation, it's a math problem. So our second round, we want to solve it mathematically. Try to find the math formula. If you have formula, then you can do much faster. So if you have a math formula, you can do much faster than the algorithm way. Algorithm way, still you need to do calculation. The math way, the formula, you just calculate. Plug in the numbers, do the calculation. Much faster. All right. Mathematically, derive a math formula. All right. So so let's do the first round. So let's delay the second part. The first round, we can write a recursion implementation as simple as this, right? Look at the code. The function body, only 3 lines. The first 2 lines, just the initial values. And the last line, the main line, we do 2 recursive function calls. Then we return the correct result. All right. Can you see? So now after we find this, this is our first solution. After this first solution, can you see anything, anything you feel not very good? Can you see something? Because we want to have a good algorithm. We always want to find a good algorithm. How about this one? Do you feel this one is a good one or not? Think about that. That's our first important question in this part. Okay? Yeah. Is it good one or bad one? Okay? Yeah. It looks quite natural, right? It's quite natural. But is there some big problem? If you do it in this way, will you have some big trouble? Think about that. Okay? Yeah. So let's try to understand. All right. Yeah. All right. The answer is a very bad one. This algorithm is very bad. Very slow. Okay? Very slow. How slow? How slow? That will be our second project, programming project. Okay? I ask you to do comparison. The first implementation, you will implement in this way. Okay? The first implementation in this way. So you can imagine how slow it is. How slow it is. Okay? Yeah. Yeah. So here I can give you some idea how slow it is. I did experiment before, because for different computers, so your response time could be different. Oh, Evan?
Because it has two separate recursions.
Mm-hmm. Yeah, yes, because of that. But we need to understand deeper. Why two separate recursions we get this kind of trouble. Okay? Yeah. Some hidden big problem inside. We need to see that. Hidden big problem inside. We want to see it. All right? Yeah. Yeah. Before that, I want to give you some, real world experiment case. Example. Yeah. Here, just my experiment on my machine. So your experiment could be different, but just you get an idea. Okay. All right. So I evaluate when n equals 45. Fibonacci number. N equals 45. Is Fibonacci number, how long do we need to find it? 45 is not a big number, right? So you can imagine how long you need to take. Okay? Yeah. All right. More than 30 seconds. More than 30 seconds. Okay? Yeah. Yeah. Less than 1 minute. Less than 1 minute. More than 30 seconds. Okay? Yeah, typically in that range. That's very slow, right? Yeah, yeah, because 45, you can imagine, only 45. Because later you will see, can you imagine when n equals 1,000? How slow it is. 45 already that slow. Can you imagine 1,000? Yeah, yeah. Later, we can even try n equals 10,000. If we use good algorithm, right, good way, in seconds, yeah, or even less than a second. This case, you get the answer immediately, all right? Less than 1 second. 1 second. Immediately. Okay? How much is the difference? Yeah. Think about that. How bad it is. That means this algorithm, this is useless. It is useless. Okay. Yeah. So next we want to understand why it is so slow. Yeah. All right. So let me show you. Yeah. We need to do here. I draw a diagram to show you why it is so slow. Yeah. All right. Direct recursion. Here we use direct recursion. Yeah. Yeah. Straightforward or brute force because we do nothing special. So it is a brute force recursion. Okay. All right. Yeah. Yeah. So here I want to draw a recursion tree. I do not need to use a large number. 45, too big. If I draw recursion 45, that's huge. Big tree. Here I only draw n equals 6. Fibonacci number n equals 6. So you can get an idea. Yeah. In order to find f of 6, fiber of 6, you need to get two values, fiber of 5, fiber of 4. Yeah. You're putting stack, right? Remember? We push into the stack. Yeah. Fiber of 5, fiber of 4. All right? Then, in order to calculate fiber of 5, you need to have fiber of 4 and fiber of 3, two values, in order to get a fiber of 5. And this side, you need a fiber of 3 and a fiber of 2, and so on. Yeah. That, all the way down to the bottom. Yeah. Because when you reach the bottom, 0, 1, 0, 1, all these initial values are given. So you can plug in, right? Initial values. Then you move up, level up. Okay? Finally, you get this fiber of 6. That's the diagram. Okay? The basic computation process. Yeah. Yeah. Evan, can you see some interesting property here in this tree?
I mean, the idea would be to make it only go to every number once.
Yeah, yes. Yeah,
You would have to do all the repetitive stuff.
right. Yeah. You can see the problem immediately, right? Yeah. Because many nodes repeated multiple times, right? Yeah, so here, I just use one special node. Yeah. Fiber of 2, how many times it is repeated? Yeah. That means you have a lot of redundancy. In this calculation, you have too much redundancy. But this is a small tree for fiber of 6. How about the fiber of 45, right? Although 45 is a not big number, but you can imagine the redundancy is huge. Yeah. Most part of the tree redundant. Most of the nodes in your recursion tree, it's redundant. Okay? That's the reason it is so slow. Okay? Yeah. All right. Based on this observation, yeah. What is your idea? How to improve? Yeah. We want to improve. Yeah. Yeah. So can anyone say something about the improvement? Yeah, we plan to improve it. Matthew, how do you want to improve it?
Let's try to set up an algorithm where we only have to calculate every node one time.
Yes.
And we can reuse that.
Great. Yeah. So that's the intuition, right? But that intuition exactly what we need to do. Yeah, that's what we need to do. Yeah. So that idea is great. Yeah. Yeah. But the question, how to make it happen? That's the second question, right? How to make it work? Yeah. Yeah. What he said, we want to remove the redundancy. Each fiber number we only need to calculate once. We only want to calculate once. Yeah. Not more than once. Okay? The second time we should stop. Okay? Yeah. Well, only each fiber number exactly only once. But how do we control? How do you set some special, protection or, some way prevent doing the second calculation of the same Fibonacci number? That's important, right? Ivan? Yeah.
Bring back the last number for each one.
Yeah, good. That's a good idea. What he said, yeah, because we want to start from bottom, right? Because we know the values. Yeah. What he said is a bottom up. Yeah. People call that method top down and bottom up. Okay. We have two ways to solve the problem. One is the bottom up. Second way, top down. bottom up. Yeah, let's do both ways. Okay? Yeah. What he said, yeah, it's a good solution. That solution, we can eliminate redundancy, all the redundancy. Yeah, let's do that first. Bottom up approach. All right. So the next, let's implement the first idea. It's a bottom up idea. Okay, all right. Method one, yeah, iterative algorithm. Because when you do bottom up, you have to do iterative way, right? Yeah, yeah. All right, so let's write a for loop. Initial value, so we create an array, F array. Yeah. F of 0 given, F of 1 given. After that, we run a for loop. Yeah, because this is the bottom, right? Yeah. So that is the bottom. So we start from the bottom, then we're going up. So after 1, then we 2, and 3, 4, and so on, right? Then at the end, we reach f of n, and this way, each f number we only calculate once, right? We never do second time calculation of the same f number, right? Yeah. So redundancy is gone. Yeah. So if you compare this version with our previous version, this one much faster. This one is much faster. Yeah. All right. Then, question. Yeah. Performance-wise, this is very good. Performance-wise. Yeah. But can you see any problem, any limitation? So this method, based on what we have learned so far at this point, can you see any limitation? Limitation, yeah. Here, we're satisfied with its performance. Yeah. But here we look at from a different angle, okay? Is there any limitation? Think about that. Another question. Yeah. This is an iterative algorithm, right? Comparing iterative implementation and the recursive implementation, what is the limitation of the iterative implementation? This is not recursive. Yeah. So now we need to compare it with the recursive. Any limitation there? Limitation is it lost the power of recursion, right? Because if you do not use the recursion, many complicated problems without using recursion extremely hard, right? Remember our Tower of Hanoi problem, okay? Without recursion, how can you solve Tower of Hanoi problem? Think about that. Yeah. So you have the potential, you may lose the power of recursion. That's the limitation, okay? Lose the power of recursion, that's big. We don't want to lose the power of recursion. Okay? Yeah. So that's why we need to take the second approach, top down. Top down, we can keep the recursion, right? Yeah? Top down, that's the recursion way. Okay? Yeah. So this time, our second method, we want to keep the recursion, but remove the redundancy. A little more challenging. Yeah? Our goal, we want to remove redundancy, but we don't want to do this bottom-up way. We want to do top-down way and without redundancy. Think about that. Yeah. Yeah. This time, our second solution, very important. Yeah. All right. Any idea? I want you to say something, okay? At least say something. Yeah. So then we have some discussion. Yeah. Hey, Bill, John.
Does recursive have to be top to bottom?
Recursive usually top to bottom, right? You start from the end, right? Your goal, right? The one you want to find. Because unknown, then you're going down, okay? You reduce the size. So that's top down, okay? Yeah? Yeah. For a bottom, it's not not recursive. Okay, yeah, because you don't need a recursion. Yeah. All right. Yeah. So here, top down. Yeah. Yeah. Recursion. Yeah. Yeah. Anyone say something?
Is it possible to do a method of recursion where instead of splitting the two numbers into two different recursions, you can just do two inputs into one, like to
We don't want to change the structure. Okay? We keep that structure. Recursion, yeah, because recursion is so powerful, we don't want to change anything in that recursion. Okay? Don't touch it. Same formula. All right? Yeah. But what you can do, you need to manage, you need to control your data. Manage your data. Okay? Manipulate, wait, organize, okay? Manage, control your data to remove the redundancy. John, something?
Is there a way to like store the value you get from two and then like check it?
Yeah. Super idea. That's the main point. Store, okay? Yeah. Store the intermediate values. Yeah. Then check. What? So these two important keywords. Yeah. He got that. Got both important keywords. Store first. Then for the new evaluation, you need to check if it's already available in your you can call it. Yeah. People call it dictionary. Okay. You store your intermediate data in a dictionary. So we need to build a dictionary. So some people call it dictionary method. You construct a dictionary, okay, to store your intermediate data. Yeah. All right? Every time when you need to calculate a new Fibonacci value, you look up in the dictionary. Is it available in your dictionary? If it is, return it, right? You don't need to do anything, just return the value. If it's not in the dictionary, then you do the new calculation. Then no redundancy, right? Because you never need to calculate it the second time. You only need to calculate the first time. Then it is available in the dictionary. All right? Yeah? The second time, pop up or whatever, return from the dictionary. Then you're done. You can keep the recursion, right? Yeah, that's a brilliant method. Yeah, it's simple, but this idea looks simple, right? But it is a very important type of algorithm. This idea is called dynamic programming. Dynamic programming. So in our textbook, we have one whole chapter about dynamic programming. Okay? Yeah. Chapter 8, one whole chapter. Yeah. But we cannot cover that. Yeah, because this is an undergraduate course, so we do not do the dynamic program. It's a graduate level course, dynamic program. Okay. Yeah. But here I give you a simple introduction to the dynamic program. This idea is simple, right? Yeah. John can easily, tell us, right? Yeah. All right. Method 2. Recursive without redundant. So use an array to store calculated value. Our dictionary is just one array. That array is our dictionary, okay? Yeah, all right. Make sure that no value is calculated more than once. Yeah. You need to compare the value, with your dictionary, stored in a dictionary. Yeah, John?
How much more efficient is checking versus like doing comparison, I guess, or
Comparison, yeah. Comparison should be faster than multiplication.
yeah.
Yeah. Checking, comparison, yeah. Comparison very fast.
Is it faster than? So is checking going to be the same? Like, is that going to be the same as comparing?
Right, same. Yeah. Checking, that's comparison, right? How do you check? You do comparison. Yeah. You do comparison. Yeah. All right. So that is the idea, dynamic programming idea. Yeah. It's a big idea in computer algorithm, dynamic programming. Yeah. All right. Yeah. So here, let me look at how much time I have. I need to control the time. Yeah. All right. The terminology. Yeah. So the programming here. So what's the meaning of programming here? Yeah. We do programming. Okay. What's the programming here? Yeah. Dynamic. We know. Yeah, because your data, is dynamic. You generate your data. Populate your dictionary in that dynamic way. Yeah, but what's the programming, the meaning? It's not our usual programming, okay? So we write a code, so that programming. It's not that meaning, okay? Yeah. So because this idea is a very old idea. Yeah. So, dozens of years ago, yeah, it was already available. Yeah. All right. Programming, yeah. At that time, that means drawing a table. Tabular. Okay? Yeah. So you arrange your data in a table. Yeah. So that's the meaning of the programming. That's the meaning. Okay? Yeah. So you create a table. You make a table. Then arrange your data in that table. So that meaning, that's the programming. Okay? Yeah. Not write the code. Yeah. Okay? So dynamic programming, so you maintain a table. Yeah. So here, this table is used as the dictionary. Okay? Yeah. Table is a 2D. Okay? Yeah. Table is a 2D dictionary. All right? So it's a 2D dictionary. Yeah. But for this problem, we don't need a 2D dictionary, right? So this problem, we only need a 1D dictionary. All right? Yeah. Then for more advanced problem, you may need to use a 3D dictionary and so on. Okay? The dictionary can be, multi-dimensional array. Multi-dimensional array. Could be that. But most of the time, 1, 2, 3, up to 3D should be enough for our real world problems. Yeah. It's rare to even have 3D dictionary. It's rare. Okay? Yeah. 1 or 2. Most of the time you need 1 or 2. 2D dictionaries. Table. Yeah. All right. Let's continue. Yeah. Yeah. The essence, no repeated calculation. Yeah. All right. Then, implementation details. Here you still have a question, how to avoid checking and the redundancy, right? Yeah, redundant. Let's look at the implementation. Yeah. Dynamic programming. Yeah. All right. Yeah. All right, yeah, so here the main points. Yeah, I put here, yeah. Then the code, you can see the code. Yeah, we need to do a little more, but not too much more. All right, so we create an array dictionary, our 1D dictionary we call the known F. Yeah, from the name, the known values of Fibonacci numbers we store in this array. So we call it known F. All right, give an input I. We want to check if the known F value is greater than 0. We initialize the known F array, all 0 values. At the beginning, this array, all the elements take 0 value. That means all unknown, right? If it's a 0, the value is unknown. But after we find the value, we assign a positive Fibonacci number to one of the elements. It becomes greater than 0. If it's greater than 0, it means that this value is known, right? That's the checking. John, this is the checking step. Okay? Yeah. So this line, checking step. That's simple. That's very fast, right? Much faster than multiplication. Okay? Yeah. All right. After that, yeah, because if it's unknown, because if it's known, you're done, right? You do not need to move to the next line. If it's known, you return it, you're done. Okay? Yeah. Oh, now, only when it is unknown, then you need to go down to implement, right? Yeah. So you still do the recursive call. Yeah. Still do recursive call. It's fine because we have the protection. We have a protection layer, so you don't worry about these two recursive calls, right? Evan? So it's safe. These two recursive calls, no problem. You keep them, okay? Because we have this protection layer, right? This layer, okay? Redundancy protection layer. How about that? Yeah. So, yeah. No redundancy. All right. So then, but you assign a temporary variable s. Yeah. Before you return this s, you make it a known. Okay. You store it in a dictionary. This step means you store it in the dictionary. Yeah. So here you can see the two keywords John gave us. Yeah. One store, you do it here. Okay. Another checking, yeah, you do it here. This line, you do it. How about that? Implement dynamic programming. Yeah. All right. Yeah. Yeah. So you preserve the recursive algorithm. So you keep the power of the recursion. Yeah. At the same time, you avoid redundancy. Yeah. Although, if you compare this method with the previous one, this one is a little slower because the overhead, you need to do more work, right? Yeah. Yeah. A little slower than the previous one, but not much slower. Okay? Yeah. Just some extra preparation. Overhead part, a little more. Yeah. 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 But from the long run, for the long run, because you maintain the power of the recursion, you can do much more than the iterative algorithm, right? Many hard, advanced problems you can use this way to solve. But that one, it has a limitation. When you have some complex, hard recursion, you cannot solve. Because you don't know how to use the iterative way to solve it, okay? Just like the Tower of Hanoi. How can you use iterative method to solve Tower of Hanoi problem? Nobody can do it, okay? Nobody can do it. Okay. See the difference, okay? A huge difference. Yeah. Yeah, so that's how much we learn. So Fibonacci, the first round, okay, some very important ideas we can learn here. All right, yeah. So let's move to the next topic. Golden ratio. Now we need to move to mathematical calculation. Yeah. Math formula. This time we need to derive it. Yeah. To do it, there is an important concept, this golden ratio concept. We need to study first. All right. Let me look at time I have. Okay. All right. Yeah. Fibonacci numbers. Yeah. All right. Yeah. So this golden ratio, yeah, from this picture you can see some nice, interesting properties. Yeah. 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 So people discovered. I remember many years ago I borrowed a book from library. A small booklet. The whole book talking about golden ratio number. Yeah, all different properties, interesting stories, Yeah. So, yeah. And here you can see, yeah. First, from this, we use Fibonacci numbers. Yeah. So look at this rectangle shape. We use squares with the side. Each side of a square corresponds to one of the Fibonacci numbers. Yeah. Yeah. 0 we skip. Yeah. 0 nothing we skip. So the first square with side Fibonacci number, that 1. Yeah. F1. Okay. F1. It's 1. So we make a 1 side 1 square. Yeah. F2 also 1. Yeah. So we have 2 side 1 squares. This is corresponds to F2. Yeah. F3 equals 2. So this number F3 and so on. Okay. Then F4. So we arrange in this way. Okay. So you can see perfect fit. Yeah. Fit in a perfect way. Yeah. Yeah. All right. Yeah. So always, so you get a good rectangular shape. Yeah. Yeah. All right. So using these Fibonacci squares. Yeah. 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 Then another property interesting. So if you draw quarter arc, yeah, because each square you can draw a quarter arc, right? Yeah, inside. Yeah. With one of the vertices as the center, then the side as the radius, then you can draw quarter arc. But when you draw, you draw carefully, appropriate quarter arc, so you can get a nice spiral curve like that. Okay, very interesting. Okay, yeah. So then some people also use that famous Mona Lisa painting, yeah, using this Fibonacci number structure, try to match. Yeah. Just many nice properties. Yeah. So in our everyday life. Yeah. All right. But first, we want to see how to get that golden ratio, how to define that golden ratio. Okay. Yeah. All right. Yeah. The golden ratio, the definition is very simple. From the ancient time. Yeah. Because at ancient time, when people try to discover some new math knowledge, people discover new math knowledge, they try to think about the reasons behind. Yeah, because people try to connect. They use their intuition, but at the same time, they want to figure out some rules. What is the right way to do the math, right? What is the right way to do the math? Yeah. Pythagorean theorem, right? What is the right way to understand the numbers? Can you imagine? At ancient time, how to understand the numbers? So they connect to some heaven thing, they try to connect, because for the understanding, a lot of math properties, so they want to connect to some, higher level, things. Yeah. Yeah. And so one interesting property, so those people, because they're based on the intuition. We know intuition may not be always correct, right? Yeah. Many times your intuition could be wrong. Could be wrong. All right. So there was a big group of people. So that group, so they all love math. They love math. Yeah. So they form a Pythagorean group. It's led by Pythagoras, whatever, that person, that famous person. Yeah. That group, okay, Pythagorean group. Yeah. It's very famous in math history. Yeah. So they study math all the time. Okay? Yeah. They love math. They want to discover all those properties. Okay? Yeah. So they discover many large number of interesting properties. Yeah. Then based on their observation, they treat. Yeah. So by intuition, so they feel any number that appears in the life, in the world, can be represented as a quotient of two integers, m over n. Two integers. Yeah. Any positive number. Yeah. Any positive number. So they feel, because they feel integer is the most natural number. Okay? Integers, come from heaven thing. Yeah, so that's the most natural number. But in the real world, sometimes it's impossible to use integers all the time, right? Sometimes we need to represent something fraction concept. Okay? Yeah, something between two integers. We need to represent a number between two integers. The question is, how do you represent a number between two integers? Yeah. That Pythagorean, that group people, they propose this idea. Even a number that is not integer between two integers, but you can use the ratio of two integers to represent it. You can use the ratio of two integers. You can always do that. Do you feel correct or not? They claim it. Yeah. So this is their, conjecture. Or we call this is the, their conjecture. Sounds all right, right? Sounds reasonable, a little bit at least, right? Yeah. But it's hard to disprove it. Yeah. If you don't feel it's correct, who can disprove it? Cody? Yeah. You think there is some problem, but the question, how can anyone disprove it? Yeah. Because they feel, the reason they say in this way, yeah, because they see this is something, very natural. They think this is the natural way, because that's from God. So that's why it's natural. Yeah, it comes from God. So their understanding. So then they feel it must be that way. Okay, the natural way. Yeah. Yeah. But later, one person from that group, the Pythagorean, that group, that person discovered one thing. That person draw a square with side one square. That's simple, right? Side one square. Then that person draw one diagonal of the square. Then that person try to represent that's the length of the diagonal using two integers, ratio of two integers, m over n. How can you represent the diagonal of a unit square as a ratio of two integers? Yeah, that person try to challenge Pythagorean group. Okay? Yeah. Maybe there's some name. So here I just call it temporarily. I could be wrong, but the meaning is that. Okay? The challenge. Because this person is a good mathematician. Yeah. He's a good mathematician. He used this, he proved this diagonal cannot be represented as the ratio of any two integers. Proved. Because here we know it's a square root of 2, right? How can you represent square root 2 as a ratio of two integers? In your discrete math, you did it. You did in your discrete math. There is a number theory part, right? In the number theory part, you need to prove square root 2 can never be represented as a ratio of any two integers. Yeah. You use contrapositive method. If it can be read, then you get contradiction. If root of 2 can equals m over n, then you get, you take square both sides. Okay, m squared equals 2n squared. Okay, yeah. Yeah. Then m squared is an even number, right? M squared must be even because 2. So then you assume m even number. So let's say m equals 2k. You use 2k plug in, you get a, 2k squared equals n squared. Then n must be even number, right? Then m and n has a common factor 2, but when you choose your ratio of two integers, can you cancel out all the common factors? You cancel out all the common factors. Then it's impossible both of them have a factor 2. After cancellation, one is odd, one is even, right? So you cannot, so you get a contradiction. Yeah. So that's the proof, disproof. Okay? Yeah. So that person, showed his proof to the whole Pythagorean group. Then the whole theory, destroyed. Because they build their faith, okay? So, established on that. So then that group of people killed this guy. This guy was killed for this discovery, for this, important discovery. That's a, big story in history, math history. Yeah, all right? Yeah. So here you can see, because here, why I talk about that? Because this golden ratio came in a similar way. So people, how to define this golden ratio, right? So they want to connect to something, very natural. Yeah. The right way to do it. Yeah. So what's that? So they use two line segments put in together. Okay. One longer line segment, one shorter line segment. Yeah. Yeah. All right, A and B. A longer, A greater than B. Yeah. Then, so you also have the third line segment, A plus B. Yeah. Then they imagine some natural, what is the most natural ratio we can represent using these line segments. Okay? Yeah. Yeah. So that's their understanding of the math. What's the most beautiful way, most natural way to represent relationships in math? Okay? Yeah. So that's the people at that time, because they feel only the beautiful math is the good math. Yeah. Ugly math, so it's not good math. We should throw away ugly math. Very messy, bad form. So we don't want to touch that kind of math. We only want to work on the beautiful math. Okay? Yeah. So based on, that's their philosophy. Yeah. So they feel, A over B. Yeah. So A is greater than B. So this ratio should be a number greater than 1. Yeah. Then they try to find another ratio that is also greater than 1. Yeah. That is A plus B over A, also greater than 1. So they feel, these two ratios, most of the time they are not equal, right? But only when these two ratios are equal, that's the beautiful math. Okay? That's a nice property. Yeah. Yeah. That's the something is beautiful. Yeah. Something very nice. Yeah. So yeah, so let's try to find the ratio. Yeah. So we can represent A plus B over A, 1 plus B over A. The smaller line segment over larger line segment. Yeah. Now we want to find, A over B, that ratio. How large is it? Yeah. because that ratio is very special. Okay? Only under some very special condition you can get this equation, right? Yeah. Most of the time you don't have that equation. Okay? So they want to find what is that right time to have this equation. Okay? Yeah. So then we can solve the equation. Let us introduce a variable x. X equals this ratio. Yeah. Then b over a equals 1 over x. So we can get a single variable equation, that is x equals 1 plus 1 over x. Yeah. We only need to solve this equation for x. Then we know the ratio. So that ratio, yeah, so they treat, so that's a most natural, most beautiful ratio. How about that? Okay, yeah. So that's our ancestor. Those people, they think in this way. Okay, their philosophy, their understanding. Yeah. All right, let's solve it. Yeah. This time, after we remove the with the common denominator, we get a quadratic equation. X squared equals x plus 1. Now we need to solve this quadratic equation. And we know we have a quadratic formula, right? So let's write the quadratic formula. Yeah. For a standard quadratic equation. This is standard quadratic equation. And its leading coefficient cannot be 0. Otherwise, it's not a quadratic equation. And this is the quadratic formula. Two possible x values, yeah, plus minus. Yeah. Two values, one for the plus sign, one for the minus sign. All right. Yeah. Yeah. Now we can plug in because we know ABC, right? A is 1, B negative 1, C is negative 1. Let's plug it into this quadratic formula. So you get x equals 1 plus or minus root 5, the whole number divided by 2, right? Yeah. So you got two possible solutions. Yeah. One is one is 1 plus root 5 over 2. Another is 1 minus root 5 over 2. Yeah. But we need to go back to our ratio of two line segments, right? Remember, the meaning of x is the ratio of longer line segment over the length of the shorter line segment. Yeah. But we know at least the x should be positive. This ratio should be positive number, right? Yeah. But if you use the minus sign here, you get a negative number. 1 minus root 5, it's a negative number. And the ratio cannot be a negative number, right? So we should drop that negative number as the solution. Because it cannot happen. It cannot happen. So at the end, our conclusion, x has to be equal to 1 plus root 5, the whole number over 2. Yeah. So then the ratio of those two numbers, when it equals this special number, then you get that nice equality. Okay? Yeah. Nice equality. So they treat that's some beautiful math property. Yeah. Okay? Yeah. So later, so people call it golden ratio. Yeah. Golden ratio. Okay? Yeah. All right. Yeah. Yeah. So you will calculate, infinite number of digits after the decimal point. Yeah. But usually people just take the first 3 digits after the decimal. And this number is an irrational number. Yeah. So here, because the exact number after that infinite number of digits infinite number of digits without cycle. Without cycles, yeah, because 0.33, 1/3, infinite. There is a cycle, right? Yeah, 3. So 1/3 equals, yeah, and 1/7, another cycle, right? Yeah, 1/7. So this is one cycle, okay? Then repeat. The same cycle, keep repeating forever with cycles, okay? But this number, golden ratio number, no cycle, okay? No pattern, repeated patterns, cycled pattern, repeated, no, okay? You know, random, it's like, you know, hard to control, like pi. In pi, yeah, no cycle, right? Yeah, yeah. So this kind of numbers, people call it irrational numbers. Yeah. Those with cycles or finite number of digits, yeah, or infinite with cycles, those are rational numbers. Right? Yeah. So there, the Pythagorean group, they claim, so the number that can be represented the ratio of two integers, m over m, this number is only the rational numbers. Only rational number can be represented as a ratio of two integers. For irrational, root 2, square root of 2, it's irrational. Irrational number can never be represented as a ratio of two positive integers. Yeah. That's our current understanding. But at that time, those people, they didn't understand the irrational numbers. Yeah. Okay? Unknown. Irrational numbers. Unknown. Okay. All right. Yeah. All right. Yeah. So there, so this, you know, golden ratio. Yeah. Then the last thing. Yeah. So why would? Because our goal, we want to calculate, we want to find the formula of the Fibonacci numbers. But why we talk about the golden ratio, right? Yeah. So it looks like, you know, two different things. Yeah. So here, let me give you the formula for the Fibonacci numbers. Yeah. Because it's like a magic formula. Yeah. Yeah. Because a lot of things we couldn't understand. Yeah. So that's why. So we may feel it's a magic formula. Yeah. All right. The nth Fibonacci number equals 1 over root 5, parenthesis, times golden ratio. This phi is the golden ratio. Yeah, because we don't want to copy that, you know, relatively large formula. So we need to use a special Greek letter phi to represent the golden ratio. Okay? So the golden ratio phi to the nth minus -1 to the nth over and phi to the nth. Then, we know irrational number after subtraction divided by root 5, another irrational number. Then suddenly we get an integer. That integer is the Fibonacci number. How can that happen, right? How can that happen? Yeah. All right, yeah. Yeah, all right, yeah. So let's stop right here. Yeah. The next time we will derive this formula, all right? We will, you know, review our discrete math, the knowledge we learned from discrete math, then we will study this formula, okay? Yeah. All right.